topic is simple harmonic pendulum. Pendulum, you can draw a diagram like this. You have a mass attached to a string. Here I call the length of a string L, and as long as you have mass, there's gravity acting on it, straight down, mg, and the angle the string makes with respect to vertical line, I call that theta. The part of a gravitational force that contributes to this motion is a tangential component. It's mg sine theta. It comes from trigonometry. Say this is tangential vector, mg is straight down. If you think about imaginary line right here, then this will be 90 degree. So this component is mg sine theta. And this angle is also same as this, because this imaginary line and mg is parallel. Now this force, tangential component, force mg sine theta, is always against the motion. So we have a negative sign, which is going straight downward against the motion. We have a mg with a negative sign and sine theta. But Newton says force is mass times acceleration. Now acceleration is nothing but second derivative of travel distance with respect to time. Travel distance along this arc length, I call the arc length S here. So we have second order equations, second order differential equation, mg sine theta equals m second derivative s. Here m, same m, so you can cancel it out. So we have a simpler form. Negative g sine theta equals to second derivative of arc length. Arc length is a little portion of total circumference of the circle. Circumference of circle is 2 pi times radius. Here radius I called L, so 2 pi L is circumference. So this travel distance, which is arc length, is fraction of that, okay, theta out of 2 pi. So it turns out to be theta times L. L is constant, only theta is variable. So if you plug this into this expression here, so your L is outside the derivative, only theta is in second derivative with respect to time. That equals to negative g sine theta. Sine theta, in order to calculate, we replace this with expansion using Taylor expansion. Say sine theta be a function, certain function of theta. Taylor expansion is given in this form. Numerator, we have a derivative. Evaluate the certain point value we are interested in. In this case, we are interested in small angle. This pendulum experiment is happening in small angle change. We don't go up high like a 90 degree like that, small angle. So which means we are interested in the zero value. So it's a, the interesting value is 0. And that will be divided by n factorial. N is the same as differentiation order, and that gets multiplied variable minus interesting point powered up to order n. So here x is theta because variable is theta, a is 0. So f theta, which is sine theta, if you use Taylor expansion, you can write it f0 and n is 0, which means we don't take a derivative f0. That's first term. Second term is first differentiation of a function f prime. Evaluate that interesting point, which is 0, and division by 1 factorial times variable theta minus 0. 0 is the point we're interested in, and plus third term is second derivative of function. Evaluate that 0 and division by 2 factorial times theta minus 0 power 2 equals on. Now first derivative of sine theta is cosine theta. If you evaluate it at 0, that's 1. Second derivative of sine is negative sine. evaluate as 0, sine 0 is 0, so this goes 0. Higher order terms, let's think about it inside the parentheses. Theta is small angle, so small number gets powered large number. That means it goes very small and smaller and smaller as power increase. More of that denominator, we have a number increasing with a factorial. It's 2 factorial, 3 factorial, 4 factorial. As the number increase, the factorial value increase dramatically. That means we have a small numerator, large denominator. The value will be negligibly small, so we can ignore that to approximate this expression. Eventually what's surviving is only this term. This is non-zero. All the rest is negligible or 0. F prime 0 is 1, so 1 over 1 is 1. Only theta is remaining. So we can say sine theta is approximately angle itself theta. So replace sine theta with theta. So we have a g, negative g sine, theta equals L times second derivative of angle theta. So we have this second order differential equation. To solve this equation, we use the initial equation r squared plus g over L equals 0. Easily you can write r equals plus minus complex number squared to g over L. Once you have root for initial equation, you can write the solution of the differential equation. Here we replace square root of g over L with omega, so which means omega equals to square root of g over L. So we can write the equation, the solution of this differential equation, which is theta equals some constant times cosine omega t plus another different constant times sine omega t. On the way reaching here, of course, we also use the Euler equation. If you want interested in mathematical level, a deep level, you can look into it. You will see there is an Euler equation involved. Now this answer, we can rewrite it using trigonometry identity, which is cosine alpha plus beta equals to cosine alpha times cosine beta minus sine alpha times sine beta. So here omega t you can treat as alpha, epsilon like a beta. If you expand this, you will have this expression, because cosine epsilon is constant, that's embedded in C1. Sine epsilon gives embedded in C2 as constant. Now if you look at the cosine parenthesis, this parenthesis is the angle. Epsilon is constant, omega t is changing. T is time. Time times something. This something, okay, gives you angle. Time times what is angle? Of course, angular speed, which means omega is angular speed. Angular speed is 2 pi times frequency. This frequency is nothing but reciprocal of period. So 2 pi over t is omega. But if you recall, we called omega to be square root g over L. So from this you can write t to be 2 pi times square root L over g. Now we have expression for period t. Now let's think about it. L is length over string. If L is large, which means it's long, then t will be large value, which means it will take a long time to make a one period motion. If L is small, which means we have a strong, the string short, then time value is small, which means the time period for one cycle is short time. So which means, say you have a pendulum clock. If you make the pendulum shorter, then your clock will go fast. If you make a pendulum long, then your clock will be going slow. Now let's think about G. On the ground level, it's known to be constant as 9.8. Say you brought that pendulum clock up to the top of a mountain, like a high mountain, like Mount Everest. Then this G value will decrease. Denominator gets smaller, then T will increase, which means that your clock will be going slower on the high altitude. Another case, say you brought that clock to the moon. The mass of the moon is much smaller than that of the Earth. So G will be smaller. So which means T will be larger than on the Earth. So your clock, the pendulum clock, will go slower if you bring that to the moon. Okay, it's been the simple harmonic pendulum. Thank you.